Good morning, everyone. Welcome to London. The weather is great, and hopefully everyone will have a great time at the conference. We've got lots of stuff ongoing, and we just finished 2023, and it was a great year. Certainly, the IPS is the talk of the town, as well as the European work on the data regulations. We follow that with great interest. I would be remiss to not welcome our newest member, Hungary. So another member and a few more coming along the way. So for those of you who are getting tired of coming to London in April, we have a surprise for you next year. We're actually going to Oslo, Norway. And I can, and being from the East Coast of Canada, I can attest that the lobster in Norway is just as good as the lobster in East Coast of Canada. So book your hotels, book your jet skis, book your regular skis, and make sure you come see us in Norway. I'd like to thank the staff, the board, and the General Assembly for the support over the past year. They always give me a hard time. They always push us. The staff are great, and they are all type A, so we have to tell them to get off their computers during holidays, especially over Christmas time. But again, hopefully we've met the requirements of what our members expect of us and what our community of practice expect of us. And we'll try to do the same thing in 2024. So I want to thank you all for being here. I'll be around all week. So if you need to talk to me or ask me questions, I will be around. And at this point, I'll turn it over to Kelly Carew, who will introduce our speaker.
So just before I get into introducing today's speaker, just wanted to say good morning to everyone who made the trip here to London to join us for the business meetings, as well to the community that's joining us online. I'm told that there's a good number tuning into this morning's proceedings. A little bit of information on the program this morning. So we're going to kick things off with our keynote, Anthony. And then we're going to move into our community updates. And the community update session is really about significant changes that have taken place in the SNOMED CT community since we last convened in October in Atlanta. So what will happen is we'll do a couple of community updates after our keynote. We'll observe our break at 10:30 to 11, and then we'll conclude the community updates from 11 till 12. Today, lunch will be at 12, and I do have to ask, and I ask you this now, probably ask you later as well, that everyone leave the room as promptly as you can after our session is over so we can change it over for some of the governance meetings that are set for this afternoon. So with the housekeeping done, we'll go to the main event actually, because I think it's going to be a really interesting one for everyone this morning. It's my pleasure to introduce Anthony Shek. Anthony is the lead NLP engineer at Guy's and St. Thomas Hospital here in London. He spearheads the development and implementation of AI-based NLP technologies and advises on a number of large language models in multiple hospitals across the UK and internationally. Anthony has become a bit of a fixture in our SNOMED CT community, so we're always happy when he can join us. Participated in a number of expos and also participated in the inaugural AI symposium we held in Atlanta in October. So without further ado, I'll introduce Anthony, and there will be some time at the end of his presentation for some questions.
Wonderful. Well, nice to be invited back, and nice to see all the happy faces on a Monday morning. And so I guess before I begin, I would just like to say a huge thank you to all the universities, the hospitals, the doctors, and the patients that are involved with all the work and research that we've tirelessly brought together and hopefully impacted for the better. And so today I'm just going to be talking about natural language processing, the recent advancements, and all this talk about artificial intelligence and large language models. And how does this relate to SNOMED? So just a little bit of background. So everything in a healthcare organization generates millions of data points. Every time a patient visits, every interaction, why the patient visited, every blood result, or every test or results. And this results in millions and millions of documentation and data points, billions of data points in a year. The majority of these patient record systems have been developed primarily for direct patient care. And so although we collect these billions of data points, the majority of it is untapped for secondary data purposes. So not just, and I guess it's the reusing of data that is the key purpose here. So we can do more than just use it to log what happened to the patient and patient histories. We can start using it for downstream analytical purposes. That's what I'm about to explain today. But there's a problem with this. Why are these billions of data points trapped, right? After all, we record them. Surely we should be able to see it. I guess the biggest problem is that it's a big data problem. It's fundamentally a big data problem. And what that means is, yes, there's millions of data points, but it's hard to extract and aggregate. And this is predominantly because this information is unstructured. And so a lot of the clinically valuable information, what has happened to the patient, what are the results, and what is the diagnosis and the treatment plan, is captured within clinical narratives or in these documents. And we call this unstructured data. And so this is where there's no data standardization requirements. Ideally, we would love to extract this automatically, but because there's no structure, it makes it very hard. And so if I was to ask a question, find me all the epilepsy patients, if I had a research question or a study, if I was to extract all mentions of an epilepsy diagnosis across all these documents, it becomes quite problematic. You could try and keyword search, look for all the words that contain the word epilepsy, but you can result in epilepsy clinic. This is an epilepsy doctor or epilepsy nurse, or this patient does not have epilepsy after all. So there's lots of different complications there. And so ideally, you would want a context-dependent extraction, like a really smart or intelligent control F in such a way. And in a way, doctors do this all the time, right? You can do it manually. They read through documents, patient records, and they conduct audits, and that's how they can aggregate. But if you want to scale it, how do we do this? And I guess before we go to, this field of AI, I guess why? Why do we want to move from unstructured to this kind of structured data and standards? And it's simply because I guess it's easier to analyze and create downstream reports because you can use it. And what I mean by secondary purposes, you can do things and aggregate information to do your audits, both clinical and administrative. How many patients use which service, what, why, when. Measuring quality reporting and trying to see, does your service meet those reports, meet those standards or expectations? Things like clinical decision support, safety, of course, research and population health management, clinical trial recruitment. Does your hospital contain the relevant cohort or population that is relevant for this clinical trial? Like, how do you know if it's not easily or readily, if that information is not readily surfaceable? And I guess lastly, this main second point is the interoperability of this data as well. Like, sure, you can send documents, but actually if you want to share aggregated data where you can easily exchange and share knowledge between different sites, both combining and understand, so you can understand, And so I guess the hype right now that everyone's talking about is this field of natural language processing and AI. And it's actually been around for a while, right? We've gone through many of these different hype cycles. We heard of big data. We heard of machine learning. We heard of computer vision and object recognition. Then we moved on to deep learning and then language models and NLP, and now we're in the field of generative AI. And I guess what's next? We're talking, all these words, and it's moving so fast. How do we keep on top of it? But right now, the hype is AI can read and generate text. And so the biggest hype around natural language processing is this fact that this is generative. And that's what I think people traditionally thought what true AI is. And that is when it can generate things or give the illusion that it generates things. And so it gives that almost human-like property. And what it does is it's captured, I think, a little bit of the imagination of the everyday person. It's very easy to use, and people can see the potential. Although they don't just dazzle us with their generation or text generation, but they have many other capabilities as well because of that are derived from that. And that is things like they can summarize, they can simplify, they can organize, they can rank, they can analyze, they can answer, they can question. And I guess in a way, sometimes I sit back and I wonder, what do I do on a daily basis in front of my computer as a data scientist? I generate code reports. I summarize, I simplify, I organize, I rank. So there's a bit of worry there that we, but of course, there's potential for automation. But I'm here to tell you not to be worried. I will get to that. But there's many of these companies now, it started off with this ChatGPT and OpenAI, but actually it's expanded far. There's lots of different companies now, especially the big tech, who are jumping into it and providing the foundations or these foundational large language models that they are investing hundreds of millions of dollars or pounds into. And so I guess the solution to all this unstructured and big data problem that we're having right now are we're turning to these large language models or language models. And so they belong, just to give you a bit of a background, is that they belong to this field, or as a subsection of AI called natural language processing. And it's simply just the understanding of teaching or having the computers read and understand text. And to understand and write text, these large language models, well, I guess they first must translate the words into a manner or into these mathematical equations, into a context in which they can interpret and understand it. Because if I told a computer, they had a seizure this morning, it's not going to react. I need to input it, and it's free text, I need to understand it. And it's, it can seem like magic, but I want to quickly give you a little bit of a background about how these large language models do it and the foundations behind it. And so how does it work? We're going to start from the very basics and the very individual units to this, where it splits down and breaks up language. The single unit, or the most simplified unit, is called a token. And what it does, it breaks down a corpus of text into what we call tokens. And a token may be on a word, a character level, a subword, subword being play, played, playing, or it can be paragraphs or even documents. But in this case, I'm just going to give you an example of how we've tokenized, in this example, into words. And the tools to use it are called tokenizers. And so these large language models, they're called large because they're exposed to huge amounts of data. And they are huge in size with a number of parameters to be able to encapsulate the meaning of the context or the data or the patterns of data that they're being exposed to. And so in this example, to grasp a word's meaning, you assume with this enormous amount of data sets that this AI is kind of reading or actually going through. It's understanding, and it learns the meaning of each word by understanding it and observing it in its natural context. And so in this case, as seizure is passed through many different contexts, the understanding of seizure is derived a little bit more. And so within this huge data set, we end up with, I guess, these word pairs almost, where you have other words that appear in similar contexts to seizure, which means they have some sort of relation, whereas other words, they appear very far away and they are distant. So in this case, atmosphere and seizure may be a bit further away in a medical context, and cat and seizure may be a little bit further away, although I'm sure cats can have seizures too. And so the assumption is that all of this premise is based around is that similar words or similar words with similar meanings appear and are used in a similar context. And so if I said the patient collapsed because they had a seizure, I could also say the patient collapsed because they had a fit. These words are interchangeable, so they must have some sort of similar meaning. But there are other contexts where I cannot use the word seizure. A diagnosis of epilepsy does not seizure. So yes, there's a degree of similarity here, but there is also some difference. That's why they're different words. But you would hope with enough data and enough contextual information and examples, it can start to learn these patterns or be exposed to these patterns. And so the way how it stores this relation or understanding, it stores these through what we call a vector representation. And this is just how the machines or computers actually understand language. And so as the model processes the words, it produces a vector and adjusts it based on the word's proximity to the word seizure in the training data. So words that are further away, these high dimensional positions of words that are distant, they appear further away, and ones that are similar meaning, they appear closer together. And so, yeah, what does that actually mean? So much as like you would describe the seizure by its characteristics, right? By its type, its duration, and I guess the various other symptoms and triggers. The values in this embedding or this vector representation also capsulate some of the meanings behind it associated with the word seizure. And so in this example, this word or vector embedding is 12 dimensions long. But I guess mathematically, you can reduce it down to 2 dimensions, and that's when I say this is a vector, or these are X and Y coordinates. So when I sort of move my hands, it's that sort of visualization that if it's an X and Y, words that are similar together are closer together, and words that are not similar appear further away. It's just very hard to visualize anything more than 3 dimensions. Anything more than 3 dimensions. And so these lengths to encapsulate the meanings, ideally you want them to be large enough to be able to capture the meanings of these words. Yet they can't be, but they can't be too big because then they become computationally very expensive. And so there is a trade-off here and a balance, and we've sort of settled on these sort of standards of how long these embeddings should be ideally. And so the way that these characteristics or these embeddings are calculated means that we can't really go to each of these positions and ideally figure out, well, which part represents which meaning. And this is because they are initialized randomly in the initial basis. And what is more important is the relative position to each other the other words. So in a way, dialysis and kidney can be similar together. And even MRI and dialysis can be similar together if you look at the first 4 embedding characters. And so although when I say dialysis and kidney are similar, because I guess they're both related to renal, and I guess they have a similar meaning here. And this is quite clever because although they're not interchangeable, you understand that they're both related to renal. And what I mean by not interchangeable, I have 2 kidneys, but I don't have 2 dialysis. And so I guess fundamentally how this all works and all this excitement, what really propelled this is this thing called the transformer. So without getting too much into the detail of it, the key or the main breakthrough was this idea of this attention mechanism. And so I guess I'm going to explain what happened before and why attention was so important. And I guess previous techniques used to model language sequentially, meaning that the weight of trying to predict the next word was heavily dependent on the word that came before it. Whereas what attention does, it allows you to, first of all, parallelize all the words and read all the words at once and pass it through. And the benefit of that, it allows you to take advantage of modern specialized compute hardware, and they're called GPUs. But I won't get into that too much detail. But what I mean to say, and why is it important to see and almost read it all at once? And so the importance is to understand, in this case, the word fit. It isn't just dependent on the previous words before, and it shouldn't just be dependent on in order, where the previous words are more heavily weighted to determine the meaning. It's actually, you need to kind of see the context sometimes from both sides. And it's not just from both sides. You need to understand, well, what is the weighting to understand the word fit? And this is what, in simple terms, this is what the attention mechanism is. So in this case, the word fit, there's a heavily focus in terms of deriving that the word fit is related to seizure. And it's heavily related because maybe epileptic, had, and I. So I had epileptic fit, kind of, you can have that meaning. Whereas if I remove the word epileptic and I could say I had a fit during the meeting, I mean, it could have been an emotional fit or an outburst, right, as well. And so although different words, different tokens, the attention of and the weighting of different words helps derive the meaning. So in this case, the software didn't fit our system as well. And you can see that some words are not important to derive the meaning of this at all. The, in, our, maybe some of these filler words. And so essentially what it allows you to do is just focus on the specific parts of the sequence when making these predictions. And so I guess in a very high level summary, we've covered tokenization and how we've split it up. We've covered these word embeddings, how the computer can actually read these and understand these tokens. We've covered this attention to understand the relations between these relations. And now we have, I guess, a machine understandable context, and we can have an encoded output for the machine to generate. And so this is actually the foundation in a very simple way of what Gen AI is. And this is what we've seen together. And if the task, or what this generative AI is, it's simple. As if you want to put it simply, it is just trying to predict the next token or sequence of tokens. And in a very basic way, this demonstration just demonstrates how it tries to predict the next token here. Nowadays, there's been a lot more complex and advancements in this area. So we would call this greedy search, where it's trying to predict the next word. But actually, you want to predict the next series of tokens because actually it flows a little bit better. And that's called a beam search or something like that. And so the prediction of the next best word, there is a probability because many different words can fit in this context, as we've seen. And this parameter is what we call temperature, where if you set this temperature, or you can almost call it creativity, to 0, it would always come up with the most probable, most likely word, which isn't always the best. But if you set it to 0, the outputs from these generative AI models will always be the same. But sometimes, I guess the realization was, actually, you want to have that creativity. When I ask the same question, I want it to give a slightly different answer. And so you up the temperature so it chooses and impacts the outputs, and each addition sequence subsequently affects this trajectory or the narrative that you're generating. Cool. So that was a bit of a summary, quick summary of AI. So what do we do and how have we used it in hospitals, or not just hospitals and healthcare, and how does SNOMED CT play a part? So I'm going to give you one such example here. And this is something that we've published recently in Lancet Digital Health, through and validated across several large London hospitals, and had several universities involved. And it's a product or a tool that we call Foresight. And so what it does, in the same way how a large language model can read the entirety of, it's exposed and trained on the entirety of the internet, and something like Wikipedia or YouTube and all these large data sets. Well, we've taken it from a hospital, a very domain specialized area that captures every interaction that a patient and a doctor has, or even doctor-doctor interactions and communications as well. And what we've realized is that in the same way how a large language model trained on learning and aim to try and predict linguistic patterns, we realized that this narrative or this story that this ChatGPT or these models, these large language models can produce, the same can be applied to the story of health. And the reason for this is, I guess, over time, visiting a hospital, you follow up, you attend, you're young, you're in your 20s, you're fine. And then maybe you have some illness, fever, you go back to your GP, they say, okay, you have a bit of maybe constipation. And then maybe down the line when you're 40, 50, 60, you develop neurological disorders, and there is a story to everyone's health. And the patient record in our hospitals, that it holds this longitudinal data sets. And when you can structure it, you can almost, and you use what we've done, we've used SNOMED CT to hide a little bit of the noise and reduce the computational complexity in this area. So we tell the story of each patient's health as a series of SNOMED CT concepts. And so that's where Foresight comes in. And so we take this historical data of all the procedures and medications, symptoms, diseases, all these these core top level terms. And we train a model to try and, well, let's predict, right? So we might have a lifetime of data from several patients, but we validate it by blinding several different parts to actually test, well, can you actually predict this story? Because in a way, large language models, they are trying to learn patterns in language, right? Trying to learn the grammar, trying to predict which exact next word makes the most sense. And actually, diseases have patterns. Diseases have trajectories. You take diabetes medication after you have a diagnosis of diabetes. So these are quite obvious patterns, but maybe you have uncontrolled blood sugar level, then you develop complications, diabetic retinopathy, diabetic foot. So there is a trajectory of health. And sometimes it's not as simple that each doctor can see, and it can be quite complex. And sometimes what we've realized in AI is quite good at is uncovering and unpicking these patterns. So in the same way how with clinical with these narratives, these ChatGPT can synthesize stories and text and learn from these patterns, doctors do the same, right? And they call that experience. And so that's what we're capturing, but that's what we realize, that's what we're trying to emulate here. So the first stage of this is our sort of standardization of all our unstructured text. And it's quite a challenging problem. I'm sure you've seen that with the recent SNOMED CT entity linking challenge. If you've ever done it, it's actually quite a hard challenge. It's not just about labeling, but it's understanding sometimes the relations between concepts, the different body parts to which concepts. You may have a stroke, but in which brain area that impacts the prognosis or the outcome as well. They may not have it. You may have a family history of it. It may have happened in the past. You may be at risk of it as well. So these are all modifier values that impact it as well. So we use this tool called MedCat to uncover and standardize information within hospitals. A very powerful tool that is used for many uses beyond this Foresight. But yes, this is one step of standardizing the data. And so here's just an example of how it looks like. We have over each and every visit, many different documents are produced, and we have this machine behind the scenes structuring and labeling data. We do have a whole validation process where we have doctors validating it as well. We create engagement, and in a hidden way, because doctors, what they do audits regularly. I'm sure doctors love to do audits all the time, but rather we hijack that process. And so rather than auditing 100 or 1,000 different records or all the patients that use their system, we built a system to semi-automate their audits. So rather than doing it all manually, they validate the model or a proportion of it, and they have the sign-off. And so that's how we managed to get specialist training for each and every domain. So we have the cardiologists training the cardiology documents. We have the neurologists training the neurology documents. We have the, etc. And so the idea is that's how we incorporate specialist knowledge by not paying doctors as well. But over time, we essentially can form this timeline as well with the demographics and all the different documents. And so that's what foresight is essentially. Now we've structured and have many of these different timelines, we can start training and build these clinical narratives. We can input a timeline of a new patient's health trajectory, can even input a synthetic one as well, an example. And we can forecast and ask it to forecast, well, how does the rest of their health trajectory look like? It's not going to be necessarily perfect, but it gives an idea, and I'll talk about the limitations in a second. What is interesting is that you can, taking advantage of the structure of something like SNOMED CT, you can filter out based on the hierarchy as well. Which type of epilepsy do they have or at risk of, which type of neurological disorders, which type of, we can go as high as a semantic tag as well. So diseases or medications or symptoms as well. And so right now we've got a bit of a demo available, and you can play around it yourself. There are some links that are there, and you can input your own timelines and explore the outcome. I mentioned about generating synthetic timelines as well. And so I would say have a play around and see and test out the different models that are there. Because as I said, these large language models are very good at learning patterns, which also means they're very good at learning biases in the data. And so if we add this prompt of a 33-year-old female, and we have these three, and the same prompt for these three different hospital sites, you can tell based on the speciality the differences in the data set it's been trained on. So for example, in the South London and Maudsley Hospital, a mental health hospital, it's more likely that that patient is going to have a mental health or psychiatric disorder and disability. Whereas KCH has a bit of everything, and Mimic 3 is your intensive care, and you can really see that in the data as well. But that's from a very basic prompt, just the demographics and just, what happens if a 43-year-old female entered one of these hospitals? What is the reason, most likelihood of coming in? We've learned as well that it's not only just works, it works quite well. I know that sometimes some of these statistics can seem quite low because you think, 0.7 or 8, or these 90% accuracy or even 100% accuracy is quite high. But when you're trying to predict the next single SNOMED concept that will appear in their record, actually, this is pretty good. But it gets significantly better when you say, okay, not just predict the next one, but is one of these 5 or one of these 10. So you can start thinking like, okay, this patient's come in, what are the use cases here? Maybe a doctor can have these next 10 codes. Is this, and just to maybe double check, right? Have they potentially missed something, or is there correlations here? And so the applications of these kind of tools, or these generative tools, or prediction and forecast tools, there's many of them, and they range from clinical and decision support. We spoke about clinical risk prediction. I think an interesting one that we're exploring is digital twins and virtual trial emulation as well. When you have a data set of these many patients, and you can start in the same way you can generate a story with ChatGPT about a unicorn that plays in a playground writing SNOMED codes on the sand. So you can input and change a little bit of their story to then forecast what happens to their trajectory. You have a patient that's admitted with epilepsy and certain types of seizures. What happens when they take drug A versus drug B? Or what happens if they take combinations as well? Because these patterns sometimes of combinations of drugs, combinations of comorbidities is not always obvious to a doctor, because at the end of the day, we're all different. And it's very rare that diseases occur in isolation. And so sometimes these we need the help or patterns of recognition or support of tools like AI to be able to manage this. However, I guess with that, there are limitations, right, of these tools. And it can only predict concepts that's been seen or exposed to in its data set right now. So if the model has never seen anyone with diabetes, it's never going to think anyone has diabetes. And the same thing happens with time as well. So it can, maybe predict to you when the next concept's going to be. But right now, with our current methodology, the limitation is you can't tell when it's going to happen, because that would be interesting too. If you can say a risk, when is this patient going to, or they're at queue of, they're in, maybe tomorrow, the day after, they're at high risk of a heart attack. That would be quite interesting. And lastly, I guess, of course, it learns biases in the data set as well. And so that's just one example of the potential that these tools are inspiring us to build. And it's not just me, there are research communities around the world and hospitals that are just excited by exploring this area and this avenue. And so I kind of wanted to spend the last few minutes talking about how do we actually choose and introduce these types of tools into the healthcare environment. And so the first part is really understanding the application framework and how it interacts with the users. There are various libraries, such as LangChain, which can coordinate various different models together and interact and give a useful output as well. You have the models as well. You can have one or more supplying it as well. And these are your large language models, which can be foundation models on a private data set. Or they can be foundation models from these big players, or they can be these what we call hyperlocal or specialized models, which have been trained on your local data set as well. Of course, you need data to both maybe train the model, but at least expose it to what you need going as well. I guess the fourth point, but probably the most important point, is your evaluation platform. And this is where that's why I'm not afraid necessarily of being replaced, because there's always going to be a room for domain experts to check if the model is working correctly, right? And assessing and making sure that it continues to run and operate efficiently and as it should. Because as we all know, the data or the underlying data set can drift, can change. Even our understanding of models, of medicine can fundamentally change and evolve, right? COVID-19 did not exist in 2018. And so we need to be aware and ready to build out these pipelines to be adaptable and very efficiently iterate and evaluate the performance of these tools. And I guess lastly, but not least, is definitely the deployment aspect as well. It's very easy to scale the high compute needs in the cloud, but sometimes it's not always possible because of security reasons and aspects. And I work in the NHS, and sometimes they're not the most digitally mature as well. So do we have the right deployment mechanisms there? And so in terms of if you're looking to procure, in terms of what the team should look like, sometimes these AI tools don't come fully ready packaged. And so it's something to consider as part of your AI tech stack. Does your team have the necessary expertise to overcome the gaps that maybe this tool that you're procuring falls short of? Maybe it's not 100% complete, and you need the team to piece the Lego bricks together to make something useful that that reaches your department's objectives. Next one is resource availability. Do you have the necessary infrastructure in place, both hardware and software, and how it integrates in the systems? Do you have the right training support, both for, I guess, onboarding the team, the technical talent, but also your users as well? How much training and support is needed for the doctors to be using it, or maybe even the patients to be using it as well, right? And if there is a bit of training, what kind of support requirements is needed? Of course, these things can cost money. Building a team, these large language model engineers can cost a lot of money nowadays, highly in demand. But sure, high compute, it's all in important. High compute tech tools as well can be expensive. And even if you get all that and be able to procure it, what is the maintenance cost? as well? How often or how many people do you need to actively maintain it? Because sometimes you get this great AI tool, but actually you end up having just as much workload being burdened to maintain it. So it's not really worth it if you look at it that way. Cool. So I'm going to stop there, but I hope I gave you some food for thought about some of the potentials in this area and how SNOMED, by structuring some of this unstructured data, can help a lot with this data. So thank you very much for listening. Yeah.
Thank you so much, Anthony. I think it's really interesting first to get a little bit of education in the morning, so that was really useful. A good primer for your talk, and also to get that deeper level understanding of how SNOMED can figure into this, because it's not always readily available in industry publications, et cetera, to that level of specificity for our community. So thank you so much. We do have some time for a few questions. I'm sure that this talk has spurred some of your thoughts. So I think right here. Thanks, Lisha. And I'll here. Yeah, of course.
Thank you for a very interesting talk. So my question is related to what you said about using the human subject expertise to check as an audit for the model. So let's say if the human doctor sees something that is maybe not a known correlation, not until that point, right? So how does that expert determine that it is something that is genuine but still not yet known? I mean, because computer models are very good at picking up correlations that might not have known, right? But it's true. How does the expert separate that from just hallucination from the model?
Right. And I guess, thank you very much for the question. I guess to answer that, I guess to just summarize the question a little bit, how do these experts know that the output is valid, right? And I think at the end of the day, these models, they produce an output which may not correlate or align with current ways of thinking, but these spur ideas, right? They make these, and that's why we use experts, right? And not just one. We don't use just one expert. What happens is that we spur a discussion about could this area or this unknown phenomenon that this model has now spat out, is that relevant? Is that something we should be looking into, right? And sometimes it's, yes, you're right. It's actually not related. And this is just biases in the data set, right? And so that's, or maybe, no, hang on a minute, there are patterns here. And so one such example is when we looked at first seizure events, and first seizure patients would enter a hospital. They collapsed with a first seizure apparently, and they entered A&E. I guess at A&E, sometimes you can't really tell what happened to that patient because you're not having a seizure necessarily right in front of them. If they saw it, instead they got to rely on non-expert narratives, right? And so sometimes they record that. They say, okay, they came in with a first seizure. So sometimes even the underlying data is questionable, but then you start seeing the trajectory of what happens to these patients, right? And this is the benefits of looking at these business intelligence tool at a large scale. You can follow them throughout time, and you see that, yes, some of them actually develop epilepsy, whereas a lot of them as well, maybe 50%, actually it's because of a faint or a cardiac syncope. They fainted and they can twitch a little bit. And so I guess sometimes that was example is a little bit obvious to the experts and people who are triaging who've seen it many times. But AI, by realizing and surfacing that data, what it does is it surfaces discussion. Is this something valuable of investigating, or is this not? And in this case, it was. And actually, it contributed to a redesign of the first seizure clinic and the first seizure pathway, because what happens is they would go to a neurologist, and the neurologist would say it's cardiology, and that you end up having patients lost in this system. Rather, if this is a common disease or disorder, a pathway where it's very clear that it's sometimes a cardiac syncope or a first seizure, Why not have them on the same day or next to each other, right? And so, and that's where we start to realize, hang on a minute, like we are changing the way, I guess, healthcare is delivered, and how some diagnostic tests with having the patients do earlier, and things like an EEG, the diagnostic yield is more beneficial immediately after I have a seizure, right? So in the same way, how if I have a fever, it's probably good to take a thermometer in my mouth when I'm sick rather than a week later, right? And it's in the same way. Sometimes a diagnostic test earlier on can save, and having the patient reach a diagnosis is very clinically valuable, and it has lots of value, downstream value that's applied. So that's this idea of this value-based healthcare. Sorry, I feel like I went on a bit of a tangent there, but I hope that answered your question. Yeah.
Okay, so we're going to do one online question before we go to one more in the room question. And this is from Christian Kincanen. What do you see as the role of post-coordinated semantics and the machine readable concept model of SNOMED CT in relation to large language models? For example, there is no concept code for the patient's mother has had a seizure, although the meaning can be expressed by SNOMED using post-coordination.
Right. So post-coordination is an extremely important concept, right? Because you have a lot of these contextual modifiers. In this case, we're talking about a family history or a family member having a, sorry, I don't remember the disease, but having some sort of disorder. If you had a concept or this contextual information for every single concept, you're duplicating it for the mother, the brother, for the cousin, for the grandmother. And then it's not just that, right? There's many other contextual modifiers. Negation, they did not have it, they could have it. And also, yeah, so you end up exploding SNOMED CT in terms of its size and having a code for each of these. And so I would not really recommend that. Post-coordination is a really good way of having to combine many codes to represent a new sort of meaning. And the reason why that's important, and with large language models, how it interacts is through these relational extractions, because you can have a hemorrhagic stroke, but it can be in different brain areas as well. So yes, you can duplicate that type of stroke for every single brain area, but why not easier just have brain areas and have stroke and join it together? So that's my opinion. I think we're not quite there yet. I think it's definitely, I mean, I know the field, and it's definitely an area of research. It's called relational extraction, and in SNOMED we call it post-coordination. But it's still early days for that, in my opinion, but definitely coming.
Yes, so thank you for a very interesting talk. One question is related to multilinguality. SNOMED is an international community with a lot of languages, and LLM is very good in English. At the same time, we have translated SNOMED. So how could you use LLM and the vectorization that has happened in English, plus the translation of SNOMED, to improve LLM for non-English languages?
So I've predominantly only worked in English, but the tools that I've built and the collaborators that I've worked with, they've worked in many different languages across the world. And one such collaborator was this the group of hospitals in Thailand, right? They don't just use a different language, they use a different script as well. And sometimes it's even a hybrid of English and Thai. And so, yes, there can be a lot of learnings, but there needs to be a little bit of a different structure, because languages or language structure of understanding changes. And so there does need to be fine tuning and slight modifications to these different models as well. I know right now there are these large foundational models that are multilingual, and they can certainly add a good foundation to the understanding as well. But there definitely is going to need to be some fine tuning or adaptation for each and every language here. Yeah, but I mean, in a way, yes, SNOMED CT changes of translating some of the disease codes extremely important, because some diseases or expressions of diseases are different in different languages and can capture different meanings slightly. So certainly important to still have different language, or having these countries curate their own SNOMED CT, because it can be slightly different, but somehow try and link it and map it all together as well.
We have another question online if you're okay. We have time. So this is from member representative from Malaysia. How do you see clinical large language models help in improving SNOMED? How could this be possible, for example, in validation, modeling, and detecting new clinical terms?
Yeah. So for us, we find the evaluation part and validating so crucial, because by validating the extraction of these SNOMED CT codes, or having these experts do it, it's very easy for them to realize, wait, hang on a minute, there's a gap here, right? And so there are codes that we have proposed and feedback into it as well. And there's many codes that, hang on a minute, you've got maybe left cerebral infarct, you may have right, but you don't have middle cerebral artery infarction. And so by validating and going through actually what's happening in the real world, you can change and impact SNOMED CT and feedback the SNOMED CT as well. And yeah, clinicians get quite excited by it, and maybe that process can be done a little bit faster, but yeah.
Okay, I think we have time for one more question in the room. Oh dear. Oh, we've had a nice deferral over here. Oh no, you both deferred. Potentially as well, if Anthony doesn't have to run away right away, as time for one or two questions during the break. But yeah, thank you.
Thank you for your talk. Thank you, everybody. I was wondering, being a doctor myself, you probably wouldn't like for your tokenization to have phrases. We don't use phrases. First of all, we write illegibly. Secondly, we make relationships with arrows, lists, and stuff in the patient's notes, and it's written in hand. So you're basically going from ideas put down in another form than actually simple phrases. How do you deal with that?
Yeah. So I think that's one thing that we realized, that yes, I am aware doctors' handwriting is bad, but I feel like actually it was masking how bad their spelling and grammar was. But I understand, right? It's a pressure. They are writing for direct communication, right? Sometimes they're not trying to write directly to the patient, and their job is to just get things done, get the orders done. Sometimes it's easier to write in a list. They don't need to write perfect sentences or perfect phrases. And with this data being unstructured, they use acronyms, they use synonyms. Spelling mistakes happen all the time. And then so in this case, I saw in the example that it isn't just attaching one word, it is understanding the phrase. And if you go on some of the demos, it will show you that if you had generalized, in my example, I used juvenile myoclonic epilepsy, right? So you're not just extracting epilepsy, you're understanding when you're having the model try to understand and extract the most granular term. So you're not just extracting the word epilepsy, you're extracting juvenile myoclonic epilepsy. And that's why we actually turn to SNOMED CT by having a, I guess, expert curated structure or hierarchy, where if we wanted to extract all the different terms of epilepsy, we train the model to first of all learn and label the most specific term, right? So to understand, don't label just epilepsy, label juvenile myoclonic epilepsy. But using the SNOMED hierarchy, we can say extract me all mentions of epilepsy, and this juvenile myoclonic epilepsy will attach. I can also say, well, extract me all mentions of neurology, and then suddenly Alzheimer's disease, or it could be AD, could extract. In the same case, you can go as high as disorders, right? And this patient with DMT1, diabetes mellitus type 1, will be extracted. But the word or phrase, please DM me, it's urgent, that won't be extracted if you put it on. So that's why SNOMED is actually quite a crucial part by having this structure over here. Yeah, so you're right, we don't just extract tokens, we do merge them if they're appropriate and relevant together in that way. What we haven't quite done yet, though, is this idea of, there was a question about relational extractions, and sometimes they appear in different parts of the document. Certainly a word, certainly something that's very valuable, because we may be talking about, you consider a MRI report talking about different brain areas, right? And so sometimes it's not a phrase, but actually to understand where this hemorrhagic stroke occurred, the location is in a completely different set of documents or a different document. And so that's understanding this far-fetched relation or attaching to do that post-coordination, merging it together. It's still a work in progress, but it's certainly on its way. I haven't solved it yet. Maybe someone in the room has, but yeah.
Can we get a big applause for Anthony this morning?